Well, hello, SPHS chemistry. Here is solutions video part 2. And in this one, we're just going to talk about what actually happens when the solute dissolves. Okay, we know that it's the tiniest particle. We know that the solution stays suspended. It doesn't settle out due to gravity. It'll go through a piece of filter paper. All the characteristics of a solution. But what actually happens when a solute dissolves? Why does it disappear? Why, when you dissolve sugar into water, does it disappear? Why do some solutions conduct electricity and other ones not? And so we want to look at how do they dissolve, what determines how much they dissolve, and what determines how fast they dissolve. Now there's a lot in this video. I'm going to try to go fast, but at the same time there's such good stuff in here. We just have to work our way through it. Okay? So first off, a solute can either be classified as an electrolyte or a non-electrolyte. An electrolyte is defined as a substance that conducts electricity when dissolved in water. Okay? So the question asks then, what is electricity? Electricity is defined as the flow of charged particles. Almost always we think of electricity of electrons flowing through a metal, because most wires, that's how electricity is transferred. And that's actually true. An electron is a charged particle, and in metals, if you remember, metals have that sea of free-floating valence electrons. So right here, I have a light bulb, okay? It's got two connectors right here, but it's an open circuit, so even when I plug it in, it's plugged in now, there's no light bulb coming on because it's an open circuit. We need something to close that circuit. That's what electricity does. So we know metals, this is a scupula. If I put this metal down into here and connect it, okay, and then I plug it in, whoop, now the light comes on, okay, because the electricity is being passed through the scupula and connecting it, and so we see electricity is flowing. It's the flow of charged particles. So electrons in the metal are flowing. But when we have a solution, solutions require ions. So an electrolyte has to dissolve as ions in order to be able for it to conduct electricity. Okay? So how does that happen? Well, if we take a salt crystal, salt is an ionic compound, means it's a metal and a nonmetal. Okay? So with the metal and a nonmetal, okay, we end up having the Na plus and the Cl minus, Na plus, Cl minus in this what we call crystal lattice structure, this organized arrangement of positive surrounded by negative, negative surrounded by positive. But it's a bunch of ions. This is really deep, y'all. Ionic compounds are composed of ions. Okay? Molecular compounds are composed of molecules. Okay, that's deep. You might want to write that down. So we have Na plus, Cl minus, Na plus, Cl minus. So when this goes into water, the water molecules come in and they attach each individual ion. And so the Cl minus ion gets completely surrounded by water molecules, and the Na plus ion gets completely surrounded by the molecules, and one by one these get ripped off, they get pulled in. You can see the water attaching there. They just get pulled off one by one, and so when they're all clumped together in this huge crystal, we can see it. Okay, so when I look at some salt, I can see, because there's billions and billions and billions and billions and billions and billions and billions of these ions all stuck together in one big old huge crystal, which we call a grain of salt. But when you put it into water, one by one, the water pulls them off and surrounds it. And so we end up having the water is surrounded like this and this. So if you go and you have a big old beaker of water, so here's a whole bunch of extra water molecules you put down in here. They're all just kind of floating around in there, but you're going to have a little bit of salt, Na plus, you're going to have some Cl minus, but they're not going to be stuck to one another. They're going to be surrounded by those water molecules. So you're going to have Na plus ions in solution, Cl minus, that are now free to move, and so they can transfer the electricity. So if I have an electrolyte, so if I take some water, okay, let me find it, here we go. If I have this, and I take just some distilled water, let me get out of the light here. Here's some distilled water. Matter of fact, while I'm doing all this, I'm just gonna turn that off, okay? So I have some distilled water into this beaker, okay? And I'm just going to put some salt into it. Okay? Just going to stir it up a little bit for good measure. So what's happening right now is just what we were just talking about. The Na pluses and Cl minuses are separating from one another. The water is breaking them apart, dissolving it into individual tiny little ions that are too small for us to see. So the salt is slowly disappearing. Too slowly for me. Okay? But a lot of it has dissolved. So when I plug this in, again now, oh, by the way, I want to prove something to you here. Here's this distilled water. Contrary to popular belief, pure water does not conduct electricity. I don't know if you can see it. Pure water does not conduct electricity. Okay, the light bulb does not come on. But if I take the saltwater solution that we just made, the electrolyte, when we put that in the, oh, the light comes on. That means there's ions in solution. So electrolytes dissolve as ions. Non-electrolytes, we're going to see in a second, are going to dissolve as neutral molecules. Okay? So, when it's dissolving in the water, you can see the water molecules. Now again, Cl minus, remember hydrogen is the positive part of water. So the Cl minuses on those, on the green one, oh, where's my, they're in here. Okay? In my Cl minus, you can see the hydrogens are all attached, the white, and then on the Na plus, the oxygens are what's attached because it's the Na plus and the oxygen's the negative part of the polar molecule. Okay? So, all soluble ionic compounds. What type of substance then dissolve as ions? Well, obviously ionic compounds since they're composed of ions. Okay? Bases are just really ionic compounds, but they have a special ion, the OH minus, the hydroxide ion, so it's any metal plus a hydroxide, so it's really still considered an ionic compound. It's just a special class of ionic compound. We call it a base when it's an OH. And then strong acids. Acids are the only covalent compounds that actually form ions in solution. Any other covalent compound is going to dissolve as a neutral molecule and be a non-electrolyte. A weak acid, it's weak means it makes ions, but not very many. I have right here a very dilute vinegar solution. So when I turn this on, let me blank this again. So when I have this, it's plugged in now. I'm trying to make sure I don't stick my fingers in here. And then I put this in here. You may be able to see that the light is barely coming on. Okay? Barely coming on, not nearly as bright. So there are ions present in here, but there's not a lot of ions. And so it is a weak electrolyte. Okay? So the only difference between a strong electrolyte and a weak electrolyte is how many ions are there. The more ions there are, the better it conducts electricity, the stronger the electrolyte is going to be. Okay? So electrolytes are things that dissolve as ions. They're either going to be an ionic compound, anything that's soluble, a strong acid, or a strong base. And we're going to talk about acids and bases in our last unit here. Okay? And so the only difference between strong and weak is the number of ions that are going to be present. Okay? So, when electrolytes dissolve as ions, this is important. How do they break apart? Okay? Ionic compounds, which the old school name of these are salts. So we think of salt as table salt, NaCl, but really there's all kinds of salts. Magnesium sulfate is Epsom salts. KCl is salt substitute. Any ionic compound, any metal plus a nonmetal is called a salt. Salts dissociate. That's a fancy word for meaning they separate as ions. Okay? Ionic compounds, so when an ionic compound, again, very deep, ionic compounds are composed of ions, so when they dissolve as ions. Okay? So what are the two ions present here? Well, we have calcium ion, and we look on the periodic table and you see the calcium's in the second row, so it's +2. Nitrate ion, it's a polyatomic ion, NO3, with a -1 charge, and we have 2 of those. So it's 1 calcium and 2 nitrates bonded together. Now, if I was just to kind of look at that, it's going to look like a Ca2+, and then it's going to be bonded to an NO3- here, and then an NO3- over here. Kind of like in this crystal, the Na+ is surrounded by Cl-, surrounded by Na+. So calcium is going to be surrounded by this, and then these are going to be surrounded by calciums, but it's a 2-to-1 ratio. So when water comes in and dissolves this, it's going to break these bonds holding all the ions together. But this is a negative charge and this is a negative charge. Those two things are not going to bond together. They're bonded together here because they're both attached to the positive. But when they break apart and go into solution, they're going to break apart into the calcium ion, and then we're going to get the 2 nitrate ions. So this subscript is going to become a coefficient. You get 2 nitrates. So, looking at that, okay, what do you think here? Well, what are my 2 ions that are present in sodium sulfate? Well, it's the sodium ion. If you go and you look in group 1, the first column, you'll see that Na is a +1. Na is +1 and sulfate is 2-, so we ended up having 2 sodiums to balance this out, but again, it's going to be an SO4 2- with an Na+ and an Na+. So what's this going to break up into? Maybe see if you can figure that out. Okay, hopefully you got this. You're going to get 2 Nas and 1 sulfate. It breaks up into the ions. Whatever ions are making it up, that's what it's going to break up into. Okay? So, lastly, magnesium chloride. Well, what are my 2 ions that are present? Well, it's magnesium +2 and my Cl- ion. So when it dissociates as ions, it's going to break up into the Mg2+ and the 2Cl-. But because this is the only way, these never dissolve like this. There's no ionic compounds never dissolve as together. They're always going to break apart, dissociate into ions. So anytime an ionic compound dissolves, it dissolves as individual ions. Therefore, you have ions in solution. It conducts electricity. It's an electrolyte. Now that's the biggest group of electrolytes. Okay. Now, I told you that a base is just a fancy type or a specific type of ionic compound. It always says the OH-. It's the presence, we're going to learn about this in the next unit, but it's the presence of the OH- ion in a solution that makes a base, which gives it a pH of greater than 7. That makes it neutralize acids, gives it all the characteristics. It's what is the characteristic of this ion that makes it a base, but it's going to break up just the exact same way. NaOH, the 2 ions are Na+ and OH-, so it breaks up into Na+ and OH-. Barium hydroxide, the 2 ions are barium and hydroxide, but again, we have 2 of these hydroxides, so you're going to get barium and 2 OHs. All right, so, and then an acid is, what makes an acid is the presence of the H+ ion. Okay, now, H+ can combine with any anion. It can be chloride, bromide, carbonate, chlorate, nitrate, sulfate, any ion. When the hydrogen's the first, and we learned this when we named. We recognized ions because hydrogen was the first thing combined with any anion, and the name of the acid was dependent upon the name of the anion. So an acid is any H+ attached to any ion, but these are covalent compounds. So these are sharing electrons here, so there aren't any ions. In an ionic compound, the electrons are already transferred. We have positive and negative, it's already been done. Here, they're sharing electrons, but when you put them into water, the water forces them to break apart, and when they break apart, they don't take the electrons evenly, and so H+ gets formed and Cl- gets formed. The presence of this ion in solution is what makes an acid an acid. Okay? So HNO3 is another acid, positive thinks hydrogen, so we have H and NO3, so it's going to break apart into H+ and NO3-. Okay? So the whole key is that an electrolyte, when they dissolve, they don't dissolve neutral like this, they all dissolve as ions. Electrolytes dissolve as ions, which makes them conduct electricity, makes the light bulb come on. Okay? That's really important. So if electrolytes dissolve as ions, how do non-electrolytes dissolve? Well, if we take some sugar and put it into some water, I'm going to have to dump a beaker out. Okay. Put a little bit of distilled water in here. Hopefully, you probably can't see a lot of that out of the picture frame. But I'm just taking some sugar, I'm going to dissolve some sugar now into my water. Okay? Stir it up a little bit. We don't have to get it all dissolved, but we know that some of it got dissolved. Okay? So now I'm going to go and plug this back in again. Okay? The light bulb's not on, but then when I go and I put my sugar solution in there, again, no light. Which means there are no ions in the solution. So when sugar dissolves, it doesn't break up into ions. It is a covalent compound. Covalent compounds, which are sometimes called molecular compounds, they dissolve as neutral molecules. So for every one molecule is solid, it's here. Now we can see a sugar crystal. We can see sugar when it's in our table or whatever, is because there's a bazillion sugar molecules all linked together. But when they go into water, each sugar molecule breaks apart from itself, but it stays together as an individual molecule. It's neutral, not charged, so it doesn't conduct electricity, yet the water is still attracted to it. Okay? So non-electrolytes, covalent molecular substances that are soluble in water, dissolve as neutral molecules, and therefore they don't conduct electricity. We call those non-electrolytes. Most substances that dissolve, that are soluble in water, dissolve as neutral molecules and non-electrolytes. Acids are really the only exception to that. And we recognize again, acid is the positive thing is hydrogen. Okay? So you can pause the video right now and come and do your comprehension check. Yep. Okay? So go ahead and pause it, do the check, and then come back. All right. So now we want to look at what determines whether a substance is going to be soluble or not. Why do some things dissolve in water and other things don't dissolve in water? And so when we're doing that, okay, it's really, the rule is like dissolves like. And I wish that we had more time because this is really important. Please consider taking AP Chemistry. We get into this in great detail on how things actually go about and what's going on here. But it's like dissolves like. Polar dissolves polar, and you can really add in on your notes, and ionic. Ionic dissolved in polar, okay? So water's polar, so salt dissolves in water because water's polar. Now again, remember, polar means it's got a positive and negative end. Since salt is positive and negative, the positive end of water attracts to the negative Cl- ion. The negative end of water, the oxygen, attracts to the positive Na+, and so there's an attraction there, okay? Non-polar is not attracted to polar, so there's nothing to pull it into solution, but they will be attracted to each other, so non-polar dissolves non-polar. Now, here is just a simple example. This is styrofoam. Styrofoam is a plastic, it's a hydrocarbon. It is non-polar. So if I want to go and I want to take some water and I put some water into my styrofoam cup, whether it's coffee or Kool-Aid or Mountain Dew or hot chocolate, it doesn't matter what it is, okay? But the amazing thing about styrofoam is that if you put hot things in, they stay hot. You put cold things in, they stay cold. Really, how does it know? How does it know? But that's a whole different unit. Anyway, notice, I mean, it's great. We've all used styrofoam cups. But if I take some acetone, some fingernail polish remover, okay? This is the main ingredient in fingernail polish remover. If I take some acetone and put some acetone into this styrofoam cup, okay? This is a nonpolar, this is a nonpolar, and so we eventually are going to end up having a very serious problem, okay? We're going to have a very, very serious problem as there she goes. The whole bottom falls out of this cup. Okay? It is not melting, it's dissolving. Okay? Like dissolves like. And so here's another example of that. Here I have some iodine, I2. I2 is a non-polar substance. Okay? It is dissolved in another non-polar substance called cyclohexane. Cyclohexane, so the iodine's all dissolved in here. This is some iodine in water. You probably can't see, but there's a little bit of iodine sitting down here at the bottom. Okay, there's a little faint color, just a itty bitty little bit possibly dissolved, but overall very little dissolved. Now if I mix these two things together, polar water nonpolar cyclohexane. We have the iodine in there to kind of give it some color so we can differentiate. So if I mix those together, and let me give it a good shake. Shake it, shake it, shake it, baby. That's why I teach chemistry and don't have my own YouTube music channel. Okay? But now when we look at this, this is what we refer to as two immiscible liquids, two things that are insoluble in one another. You can see them quickly separating out. The iodine, which is nonpolar, is staying with the nonpolar cyclohexane. The water is staying down here with very little iodine in it at all. And so they separate because like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Water is your most polar substance. Water is a lot of times called the universal solvent because it dissolves so many things. But there's no such thing as a universal solvent. If it dissolved everything, we wouldn't be able to have it in a jug. Okay? There's nothing that dissolves everything. Okay? So miscible, alcohol and water, you can mix those together. Antifreeze in your car. If you want to put the antifreeze, you can mix that in any ratio you want to mix it. Those are miscible liquids, whereas the oil, the cyclohexane and the water, these are two immiscible liquids. Okay? Now, so when you're taking a shower, you have oil, which is nonpolar on your skin and in your hair, okay? And you have polar water. So we actually use soap, and what soap does, it actually links them together. Soap has a polar end, it's got a nonpolar end, and so the polar end attracts to the water, the nonpolar end attracts to the oil, links them together, and washes it off. If you don't use soap when you bathe, you still stink, you're still oily, okay? So soap is what we call a fancy word, you don't have to know it, but just for the fun of it, it's called an emulsifying agent. It brings an emulsion, two insoluble things, it makes them stick together. They put egg whites into creamy Italian and mayonnaise, or mayonnaise, in both of them, to make the oil and the vinegar not separate. And so it's an emulsifying agent, just a little something for you. Okay? So, the type of bonds, whether it's polar or nonpolar, that's one thing that determines when is one thing soluble and something else not soluble. Okay? Now, the strength of the intermolecular forces between the solute and solvent, that's another factor, okay? Because this is being held together. There's called the lattice energy that is in here. So when water molecules come in and they start pulling on this and surrounding it and trying to pull it into solution, this ion to dipole, water's called a dipole, a polar molecule, this ion to dipole attraction has to be stronger than the lattice energy, the ionic bonds holding the salt crystals together. So it all depends upon how much attraction is there between the water, the solvent, is when they surround it, you know, and you just get ions all the way around and it starts pulling, is it strong enough to overcome the attractive forces here? If something is insoluble in water, that means the water's not strong enough to break it apart. But water can break apart. This ion to dipole attraction is very, very, very strong, okay? And so, it's all a matter of the attraction between water molecules and ions, which is that ion to dipole attraction is strong enough to overcome the lattice energy holding ions together. That's what it's going to be all about, okay? I wish I had time to develop that more, but we just don't. Now, let's talk about what affects, that affects how much or what dissolves. Like dissolves like, okay? Polar dissolves polar, and we're also looking at, you know, what is the attraction between the water. There has to be a strong attraction between the solute and the solvent, the water and the salt, the water and the sugar. There has to be something attracting there. And again, I would love to be able to develop that more, but just don't have time. This now is not talking about, you know, what dissolves, it's just how fast it dissolves. Now this is very obvious, we know this. If we want to try to make our sugar dissolve in our iced tea, you know, or we're trying to make something dissolve, we know that the size of the solute particles, okay? We want to crush them up. We want to increase the surface area, okay? Smaller chunks dissolve faster than big chunks. We always stir it. I had to stir that to make it dissolve. That's nothing new, okay? And so, keep going and click, click, okay? Now, how concentrated the solution is, okay? The more concentrated it is, the more water molecules that are already tied up, and so there's fewer and fewer water molecules available to try and pull these into solution. So the more concentrated it is, it slows down. And then, obviously, we can heat a solvent, much more things dissolve in hot water than in cold water, which is why you do your dishes in hot water. That's why you wash your clothes in hot water. And we bathe in hot water because it's comfortable, but it also gets the dirt off better. We wash our hands in hot water because it gets the dirt off better. Okay? So generally speaking, increasing the temperature increases the solubility. Okay, so here's another comprehension check. So pause the video here. Do your comprehension check, and then when you're done, okay, write all this down on a separate sheet of paper, because then you're going to fill it in on a Google Doc later. So, but you want to have the work, so when you check it, you have an understanding of what you're doing. Okay, because we'll go ahead and post the answers to all these after the due date. All right, now this is the next point that's very important, and this is the solubility. This is now how much dissolves. Okay. And this is really determined by how much attraction there is between the water, the solute, and the solvent. But we're not going to get into the details of that. But the solubility values are expressed as grams of solute per 100 grams of solvent. Usually it's 100 grams of water. So how many grams of sugar can I put in 100 grams of water? How many grams of salt can I dissolve in 100 grams of water? And because it's temperature dependent, okay, we actually have to have I'm going to come here. I jumped ahead. I'm going to come to this. Oh man, I'm going way ahead. I thought I had something else in here. Okay, that's going to be on the next one. Okay, so we're just going to talk about solubility. We'll get into the actual interpreting graphs and stuff in the next video. I just got confused a little bit. But hey, bear with me. I'm talking to an empty crowd. Okay? All right, so solution equilibrium. When we have a maxed out saturated solution, when solid sitting on the bottom, it's going to continuously, some's going to dissolve, some's going to precipitate out. It's what we have equilibrium. Okay, some solid sugar, sugar dissolves, sugar precipitates out. We get that equilibrium. Now, we have three different qualitative ways of measuring solubility. We can either say it's unsaturated, saturated, or supersaturated. Now, obviously, if a sponge is saturated, that means it's got the maximum amount of water. It can't hold any more. If something's saturated, that means full. So a saturated solution is a solution that's got the maximum amount. Usually there's some sitting on the bottom because you can't dissolve anymore. Unsaturated is just the opposite. There's still room at the end, so to speak. You still have some ions that, some room for solute to dissolve. Now, a supersaturated solution is a unique, rare solution. You just don't add, if 40 grams of, say, salt dissolves in 100 grams of water, you can't just put 50 grams in and get a supersaturated solution. No, what's going to happen is 10 grams is just going to sit on the bottom, 40 grams is going to dissolve. A supersaturated solution is a unique where you have more than the maximum amount, but it's very unstable. Actually, the CO2 in a can of pop is a supersaturated solution. So if you shake that up, you disturb that and open it up, it's going to come spraying. All that extra CO2 is going to come flying out. Okay? So supersaturated solution, the way you make it is you heat it up, make a saturated solution when it's hot, then you cool it down slowly. And instead of some of the solid precipitating out like most substances do, these rare substances that form supersaturated solutions, they end up just not wanting to come out of solution. So they crowd in more than what they should, but it's unstable. And so you can either add a seed crystal, add one more crystal to it, you can shake it up, which we do with a can of pop, or you can kind of stir it, and all of those will cause the extra amount to come out of solution. Now, I was going to do a demo, but I don't have time, so here is a link right here. You watch this. This is going to be a link to a video of a supersaturated solution being formed, and then when you put an extra crystal in. And so it's really kind of cool. You're missing out seeing it in person because of time and coronavirus. Okay? So, unsaturated is anywhere along here. You can add from 0 grams up to the 46, but once you get saturated, anything else that you add is just going to sit on the bottom. Okay? And again, it's very, very difficult to make a supersaturated solution. Those are rare. You can look them up on YouTube, Google. There's some cool ones when they add the seed crystal and watch it come out. Okay? So you can do that on your own. So if we have an unsaturated solution and I put a crystal into here, it's going just to dissolve because there's still room. If it's a saturated solution, okay, it's just going to go and sit on the bottom. But if the solution happened to be a supersaturated solution, which is rare, but it could have been, it's going to do what you're going to see in that video. Not only is that one crystal going to not dissolve, it's going to cause all the extra, the super amount of supersaturated, cause the extra crystals to come out of solution. So that's a test for how can you tell if a solution is unsaturated, saturated, or supersaturated at a crystal. If it dissolves, it's unsaturated. It just sinks to the bottom, it was saturated. If a whole bunch more crystals come out, it was supersaturated. Again, those are rare. All right, so there you watch that video. And so here's your comprehension check on that. Okay? Now, the last few things are what effects do temperature and pressure have on how much will dissolve? Well, pressure has no effect on a solid or a liquid. But what about a gas? Now, I love to drink Diet Mountain Dew, and I tend to call it pop. I grew up in the north, okay? Why do they call it pop? Because when you pop that top, okay, psst, you hear that, okay? You hear the pop rushing out. It's the gas, because there's normally 5 atmospheres of pressure before you open it, and it reduces down to 1 atmosphere of pressure. So what that does is it immediately, what do you see? Well, you see bubbles. Well, what does that mean? That means that gas is coming out of solution. You decrease the pressure, you decrease the solubility. Okay? So, if we have a greater pressure of the gas above the liquid, then as you put greater pressure, more is going to dissolve. Now, the two most practical applications of this are the fizz and pop. You want to keep it fizzy by keeping the pressure on it. Once you open it and lower that pressure, it immediately begins to bubble and fizz, okay, and comes out of solution and goes flat. I don't know if you've ever heard in scuba diving, seen it in movies or something, where somebody gets the bends. They come up too fast from way down deep. Well, the deeper you go in the water, the more pressure there is, and so as you're breathing in on your scuba gear, more and more oxygen and nitrogen are dissolving in your blood. And then all of a sudden you see a shark and you say, ah, and you go screaming up to the top of the water super fast. Well, all of a sudden, it's like opening the pop top. All of a sudden now the pressure is greatly released on your body, and your blood actually begins to bubble and fizz like a soda does as that extra oxygen and nitrogen comes out and collects in your joints, and extremely painful, can actually kill you. So you have to come up slowly when you're scuba diving to let your body just naturally get rid of those gases. You cannot come up quickly. Now, all of this is known as Henry's law. It says the pressure and solubility are directly proportional. Double the pressure, double the solubility. Okay? As pressure increases, solubility of the gas in the liquid increases. Okay? So, gases obey Henry's law. Okay? What happens when Hobbs opens a bottle of Diet Mountain Dew? Okay? So, you have all this dissolved CO2 in here. It's under 5 atmospheres of pressure. You open it up, okay? You see the bubbles, you hear the fizz, the escaping gas, okay? You reduce the pressure, you reduce the solubility, okay? Then that rapid release of gas is called an effervescence. And so like they have an efferdent is a denture thing that you plop it into water and it fizzes, it effervesces. They call it an effervescent tablet. Alka-Seltzer, plop, plop, fizz, fizz, oh what a relief it is. Okay, that's an effervescent tablet because it produces a whole bunch of gas. Good ACT word right there. Just the rapid release of the gas is effervescence. Okay, now this is what I was trying to get to earlier, but the effect of temperature on solubility. Okay, now we pretty much know, we already said, things dissolve better in hot water than they do in cold water. Generally speaking, okay, so watch a video here. You can stop and watch this video. It's only about 2 minutes long. It shows a guy with seltzer water, and it'll help you to be able to do this one right here. But I'm going to let you kind of go and do that, okay? And so that's going to end right now. You're going to stop, and that's going to end part 2 of our video on solutions. All right, hopefully this is helpful to y'all. Again, if you have any questions about any of this, email your teachers. We'll be glad to help you in any way we can. And again, if you're enjoying these videos, please subscribe to my channel and like the video.